Alright guys, this video is for page 20 of your interactive notebook about the quantum atomic model. And this is actually one of my favorite topics that we talk about all year because I find it absolutely fascinating. So we're going to start by discussing two key principles that helped evolve the model from the Bohr model into what we will call the electron cloud model. And the first one is the wave-particle duality of electrons. And this sounds familiar because we already discussed the wave-particle duality of light, of the photon, right? That light can exhibit properties of both waves and particles. And interestingly, the electron does the same thing. And if you're paying attention to what that means at all, it's kind of mind-boggling, right? To suggest that the electron, which we know is a particle, it has mass and a charge, and it's what makes up matter, right, along with some other subatomic particles. But it actually exhibits many characteristics of a wave. And science discovered this in an interesting way. So if we look at these two images right here, we're looking at what we call the double slit experiment. This is a famous experiment. If we have a beam of particles, and this could be anything. You can think of these as small alpha particles, or you could even think of these as marbles, right? And we're going to shoot a whole stream of them at a barrier, and there's just going to be two slits in this barrier, just two openings for these particles to pass through. And so, of course, the particles that hit those openings will pass through it, and you'll see them hit the screen, right? This is a detector screen, and it's going to glow wherever those particles hit it. And we'll get these two nice bands that are right across from the double slit. Makes perfect sense, right? Because they can only go through the openings. Now, waves are going to do something a little bit different. Because whenever the wave hits the slit, two new waves will actually be propagated at each opening, or one at each opening, rather. And they're going to overlap as they spread out, right? Because that's what waves do. Imagine waves in a pond. And on the website, there's an interesting video where this is demonstrated, actually. It's up above when we talk about the wave-particle duality of light. And it's really worth watching because it illustrates this really nicely. But each wave is going to spread outward from its point of origin, which will be the slit. And as it does that, those waves are going to overlap with one another. And when waves overlap, one of two things can happen. One of them is constructive interference, and this is where the peaks of the waves overlap, and the amplitude of the wave is increased because they add together. But the other type of thing that can happen is that the peaks of one wave can overlap with the valleys of another wave. And this is called destructive interference. And when destructive interference happens, it basically cancels the wave out. So we have two kinds of interference: constructive, which increases the amplitude of the wave, and destructive interference, which cancels the wave out. And that's why we get this interesting pattern here on the right, which is called an interference pattern, where every time that constructive interference occurs, we see a band of really intense light, but it fades out as the waves stop overlapping. And then when the waves overlap destructively, we don't see any light at all. So these two things are interesting enough on their own, but of course scientists can't wait to figure out what this means for the electron. So they shoot the electron at a barrier with two slits, and something really astounding happens. Because while we would expect that the electron, a particle, would behave just like these particles, it doesn't. Instead, we end up getting an interference pattern. We end up getting bands of high intensity, and we end up getting bands where the electrons appear to have been canceled out. But that's not how particles behave. So the scientists thought, well, maybe the electrons, because they're all negatively charged, are spreading away from each other, right? Maybe they're repelling one another, and for some reason that ends up giving us these bands. And so they shoot the electrons individually at the screen. But the same thing happens. We get an interference pattern. And at this point, there really was only one conclusion for them to make. No matter how bizarre it was, the electron was definitely exhibiting a wave property. It was definitely exhibiting constructive and destructive interference properties. And as it turns out, As it turns out, the electron exhibits multiple properties of waves. Electrons, they have wavelengths and they have frequencies and they carry a certain amount of energy with them because they're both waves and particles, right? So just like light, we call this the wave-particle duality of electrons. They exhibit properties of particles, they have mass, they have charge, but they also exhibit properties of waves, like wavelength and frequency. Added to this, we have the Heisenberg uncertainty principle. They're not really directly related, but together these things are going to force the model to change, right? So the Heisenberg uncertainty principle states that we cannot predict both the position and the speed of an electron. And the more accurately we know one, the less accurately we know another. And that's a bit of a paraphrase of the Heisenberg uncertainty principle, but it works for our purposes. And what it basically means is that we cannot describe exactly where an electron is, only where it's likely to be. This is a bit of an abstract concept. There's no real good way to illustrate this in our interactive notebook, so we're just going to put this comic strip in right here, where we have the Mr. Heisenberg. His name was Werner Heisenberg, and his wife, and she's trying to find her car keys, and he says, you probably know too much about their momentum. See, the Heisenberg uncertainty principle really relates angular momentum of an electron and its position, but we're not going to get into that. We're going to kind of paraphrase it to be speed. For our purposes, it means close enough to the same thing. Okay, so this forces a new model. Because previously in the Bohr model, we kind of took for granted that electrons were particles, and we kind of took for granted that we could determine both the position and speed of an electron. So now that we know that these things aren't true, it forces a new model, and we're going to call that the electron cloud model. It's the quantum atomic model. And it's going to define the position of the electrons with respect to it being a wave. And so instead of having these nice clean orbital paths where the electrons just orbit the nucleus like planets, because the Bohr model is often called the planetary model, instead we're going to define orbitals for each electron. And an orbital is a lot less clean. It's a three-dimensional space around the nucleus where an electron is likely to be found. It just represents all of the areas where the electron is most likely to be found, but it doesn't even have to be found necessarily within that area. The electron cloud is a bit diffuse. It just tells us where the electron probably is, not where it really is at any point. We're going to describe 4 different possible orbitals that we can have. There's the s, p, d, and f orbitals. The s orbital is going to be the simplest one. It's going to exist at every energy level from 1 up. So at every energy level that we have electrons, we're going to have an s orbital at that energy level. And there's only one of them for each energy level. So at the first energy level, I'll have an s orbital. I'll have another s orbital at the second energy level, another one at the third, another one at the fourth, and so on. And the only difference between those s orbitals is that basically they'll get bigger. So the second s orbital will be larger than the first energy level s orbital. The second type is the p orbital, and these come in groups of 3. And these will exist at every energy level of 2 and higher. So starting at the second energy level and going up, I'll add p orbitals to the model. The third type is the d orbital. There's going to be 5 of these at each energy level, and they start at the third energy level. And the fourth kind is the f orbital, and there will be 7 of these at each energy level, starting with the fourth. We're going to illustrate the s and p orbitals, and we're going to show how they overlap, but we're not going to illustrate the d and f orbitals. It is worth seeing what they look like, and you'll find them at the very bottom of this website. But we're not going to draw them. You don't have to memorize what they look like. They're interesting to see, but they're too complicated for us to need to draw. So on the left, we're going to illustrate this so you can kind of see what it looks like. And I have 3 different pictures here, and I'm going to talk about them individually. The first one over here on the left is a picture of the s orbital. You'll see it's spherical, although there is a place that's kind of hollow here because the electrons are not going to go into the nucleus, right? So this cloud surrounds the nucleus. It's spherical in shape, right? This graph has 3 axes because we're looking at a 3-dimensional representation. So this spherical shape represents where the electron is likely to be at any time. The darker regions are where the electron is more likely to be, and the lighter regions are where the electrons are less likely to be. And of course, the electron can even be outside of this boundary. This boundary doesn't really exist, right? It's just kind of hard to draw a gradient that keeps going outward. So this is the s orbital. So we'll have one of these at the first energy level, another one at the second that will look kind of the same but bigger, another one at the third, and so on. The second type of orbital that we talked about is the p orbital, and these come in sets of 3. And it's going to be very important that you understand that it looks like there's 6 of these, but each of these is 1. So this p orbital on the y-axis is called the py orbital. And even though there's 2 halves of it, it's 1 orbital. The second one is on the z-axis here. This is the pz orbital. Again, it's just 2 halves of 1 orbital. These are not separate, they're the same thing. And then the last one is the px orbital here on the x-axis. Again, there's 2 parts of it, but it's 1 orbital. So 1, 2, 3 of the p orbitals. And these will start occurring at the 3rd energy level. So we overlap these to form the model, right? These don't exist separately from one another. An atom with electrons will have electrons in all of these different orbitals. So if we look at an atom, like say oxygen, that has electrons in the 1st and 2nd energy levels, we're going to have a 1s orbital, that's an s orbital at the 1st energy level. We'll have a 2s orbital, which is electrons in the s orbital of the 2nd energy level. And then we'll also have the 2p orbitals. These are the 3p orbitals that exist at the 2nd energy level. This 2 stands for the energy level, not the number of orbitals. P's will always come in sets of 3, but these 3 happen to be at the 2nd energy level. And of course, we could keep making this atom bigger. We could add a 3s orbital at the 3rd energy level. We could add a whole nother set of p orbitals. Those would be the 3p orbitals at the 3rd energy level. We could add d orbitals to this, but those are going to look really, really weird. So again, please feel free to check out the wave-particle duality videos. There's one for light and there's one for the electron. Both of them are worth watching. Please check out the d and f orbitals on the website. You can actually blow up the pictures and it has descriptions of them as well, and those are definitely worth seeing. Other than that, you're done with page 20 of your interactive notebook about the quantum atomic model.